Hi everyone, and welcome to the fourth and final lecture. We are very lucky to have Alexander Givental giving a mini course in quantum Riemann-Roch. I hope you enjoyed this final lecture. Please go ahead.
Thank you. So let me remind you where we were in the end of the previous lecture. It was last week. So we're talking about properties of genus zero Gromit invariants, the general intrinsic properties due to universal relations between Gromit invariants, and usually such relations formulated as an infinite system of some quadratic third-order partial differential equations. But we found the geometric formulation of it, namely, so if you take the graph of differential of this genus zero descendant potential, then it is such a what we call big J function. So it is so it can be understood as a Lagrangian submanifold in the symplectic loop space. So this curly H is the space of Laurent series in one indeterminate Z with coefficients in vector coefficients in the cohomology of the target space. And so that's how the graph of differential looks explicitly. So there is what's called the dilaton shift. Then there is the input that's power series in Z with coefficients in the cohomology. And the rest is the principal part of Laurent series. That is, if you expand this expression as the geometric series, so it will be Z in denominators. And so these are the Gromit invariants where the input is determined by this power series part. So so this black thing, it's supposed to be that Lagrangian submanifold parametrized by the space H plus of power series, such series T. But what we established is that it has very special properties due to those universal identities, namely this L it's an overruled Lagrangian cone. More specifically, it means that its tangent space T is its tangent space at some smooth point. Then first of all, this tangent space is invariant with respect to multiplication by Z. So it's a module over the power series, scalar power series in Z. Then if you take this Z times T as a subspace, and actually it lies in that Lagrangian submanifold. So the Lagrangian submanifold, therefore it is a cone with vertex at the origin, as this picture suggests, but it's not just ruled by lines, it's ruled by in such infinite dimensional spaces with finite codimension. And moreover, if you take any points in this space, so then the tangent spaces to the cone at such points in one ruling space, it's the same tangent space, that space T itself. But now we will combine, so the plan is therefore to use quantum Riemann-Roch theorem together with the intrinsic properties of this zero Gromit invariance, in particular these properties, in order to derive consequences which, such as various mirror formulas in Gromit theory. But we need one more ingredient. Namely, so far, the variables Q, which are this Novikov variables, these monomials, which play the role of just, there are to distinguish contributions of curves of different degrees. They were on the background. It was just the ground ring in all these considerations. But now we will employ some relations that involve these Novikov variables, and it's called the divisor equations. So here is maybe really familiar diagrams of this modular space of stable maps. It works in genus G as well. This is a universal stable map diagram, and we discussed with you string equation when you take the class 1 and push it forward here. But this time we do the following thing: we take a degree 2 cohomology class of the target space, pull it back by evaluation to this family of curves and then integrate over fibers. And so we'll get something here, but that something should be degree 0 class when you push forward along the family of surfaces, remaining surfaces from degree 2 class, get a constant, and it's easy to see what that constant is because it's just the value of that homology class P on the homology class of the curve. So it is just, if you wish, the degree of the curves, the degree D with respect to that degree 2 class, or if you represent it by Poincare dual hypersurface and its intersection index of curve with the hypersurface. So it's constant. And as usual, if we can ask this question, so we could have something to be integrated over that space, but we pull it back to that space and multiply it with P and ask, okay, what is this new integral? And the answer is, well, it is this number times the old integral. That means that we have some, the fact that we can ask a new question, but we know the answer a priori means that we have some relation between Gromit invariants, some constraint on generating functions. And if you go through this formalism of generating functions, that what will be the answer. So so there is some basis in second homology group, so that we measure the degree of the curve by the string of coordinates of that homology vector, and then we take in the second cohomology, take a basis dual to that basis in homology group, so these P's are dual to the basis in the homology for which these degrees are computed. Then and this D is the total descendant potential of the function. Then this is a relation actually that what we'll get from this consideration. So in this case of the string equation where P was 1, then found that it is 1 over Z hat, so the quantization of the operator of multiplication by 1 over Z in the loop space applied to the total descendant potential is 0. And this time we have a different operator. It's this class Pi, one of these divided by Z. If you quantize that corresponding quadratic Hamiltonian corresponding to this operator, then and apply it to D, then it will be not 0, but it will be the same as differentiating in this Novikov variable. That is, it means that multiplying whenever you have this monomial, multiply it by Di. And there is some anomaly that comes, some constant that comes from genus 1, but we're interested mostly in genus 0, so it doesn't matter really what is there. So the genus 0 consequence of this is the following, that, if so that well, there's the fact that this D is invariant under quantization of this, sometimes quantization of this operator, then it means that the not invariant, it's annihilated by it. It means that the function f naught hidden there, it comes from genus 0, will be also annihilated by it. But if we talk about the graph of differential of that function, it means that that graph, that L, that Lagrangian cone, will be invariant with respect to the flow of this vector field. So if you take a point F in the loop space, it's a Laurent series with vector coefficients, and apply this operator to it, then you'll get a vector, right? And altogether, this operator defines a linear vector field in that symplectic loop space, except that now that symplectic loop space, that Q's are considered not as constants, but this is that it involves differentiation in this variables Q. Therefore, it is linear vector field, but over actual constants, over rational numbers. So in this incarnation of the symplectic loop space, so this is such vector field, and the point is that it's tangent to the cone. That's what it means, that the function whose graph of differentials is L is that it is annihilated by this operator. And annihilated means that Yeah, if you take the quadratic Hamiltonian, then the quadratic Hamiltonian should vanish when you restrict it on this Lagrangian submanifold, or in other words, that this vector field is tangent to it. There is a kind of very serious consequence of this, namely, so let's consider the ruling spaces. There was this cone is filled by some finite parametric family of these infinite dimensional ruling spaces, which are z times tangent space at every point of it. Or it takes the tangent space itself at some point. So, of course, they are invariant with respect, by definition, with respect to multiplication by variables q's. It's just it's a module over the Novikov algebra of Novikov algebra of the variables q's. But it turns out that they're invariant also with respect to differentiation operators, where more specifically, therefore, let's consider. So this kind of differential operators, as I already told you once, so this is actual differentiation. Z plays the role of Planck constant. So this is derivative in logarithm q, but we are talking about vector valued functions, and so this usual representation of the algebra of differential operators in Novikov variables can be twisted a little bit by using these matrices of multiplication, classical cohomology by this classes pi. So it is the same algebra acting slightly in slightly twisted way. But so let's consider this some kind of differential operator. It's non-commutative expression. Q's don't commute with derivatives. And so I think that the tangent spaces are invariant with respect to such operators. That's what this means, right? So you take a point f in the tangent space, and you apply. You see that there is, so you apply that operator. So you take point f in the ruling space, apply this operator, you take tangent, we get vector in the tangent space, multiply by z. I see that this differs from this expression by z. We get again a point in the ruling space, or the ruling space are invariant with respect to such differentiations. Therefore tangent spaces, which differ from them by just multiplication by z, are also invariant, so already modules. But if you place such operators, then they kind of preserve each ruling space, right? So each ruling space is a D-module. But moreover, if you consider, we consider what is here is just exponential of such an operator, or you can think of it as a flow of a vector field defined by this operator. So this is now divided by z. Then the whole cone is invariant with respect to it. That is, therefore, this is, you can think of it as one parametric group of transformations in the symplectic loop space, and this time the ruling spaces are not preserved each one, though they move from one to the other, but still the whole cone stays invariant. And so therefore there is this huge infinite dimensional group of symmetries of operators of transformations which preserve this cone, but they act with respect to Novik, in the direction of Novikov variables. And so the reason for this is the following. So if you take a point f in the ruling space and apply this operator, then as I said, you get the point in the ruling space, it's a D module. But if you divide by z, therefore, you get the point in the tangent space, which means that the vector field defined by this operator d divided by z is tangent to the cone. And therefore, it's one parametric group, exponential of it is also, therefore, preserves the cone itself. Any questions about this? There is here is some kind of cute argument similar to this, which is about is a proof of genus zero Virasoro constraints, but maybe let's discuss if the time will be left in the end, because it actually it's rather perpendicular to what we are planning to discuss now. So I inserted it here just for fun, but maybe let's see if the time permits. In the end, we will return to it, but I'll skip it now. So for kind of that's the point now. So if we use this simple, that's the geometry topology behind it, just to integrate to form pulled back from the target along the fibers, and you know the answer, it is just some scalar. And the consequence of that for the generating function and for the Lagrangian quantity is this huge infinite dimensional group of transformations which preserve this Lagrangian cone. Any questions? Then let's go. Let's go on and extract some consequences. Now, what we're going to talk is what's called quantum Lefschetz theorem. It is a general result, but it's maybe the best thing to explain it is just illustrate it in one example, and it will be clear what it is in general. So here is an example. We're talking about complex projective space of dimension n-1 is the target space. P is the hyperplane class, so it's degree 2 class. It generates multiplicatively the cohomology algebra of it, so P to n is equal to 0. The expression which is written here, it is the small j function, so it is therefore it is 1 point on that Lagrangian cone of the theory. If you think of Novikov variables as just constant, it means that as a ground ring. So over that ground ring is just 1 point. So at the point in quotation marks, now it varies with Novikov variable, but still it is, well, in our original point of view on the loop space as a just space of Lorentz series with values in cohomology, it is 1 point there. The reason, there are many reasons why we know why this expression is there. It's some kind of hypergeometric expression. It satisfies this differential equation, and its symbol is it's a relation in quantum cohomology algebra projective space. So it's not hard to figure out what's quantum cohomology, and there is logic of general logic of the theory tells us that yes, we're already familiar with this expression for various reasons. We know that it is it does represent Gromit invariance of a projective space. Now, suppose that we want to know Gromit invariance of some hypersurface X of degree L. So that's why it's called quantum Lefschetz. It's about Lefschetz hyperplane section theorem. We know something for the ambient space, and we want to derive some conclusion for hyperplane section with respect to some degree L line bundle over the projective space. And the claim is that if this is a point in the cone of the projective space, and this expression, so you see that's modified by some factorial products. Here, this expression lies in the cone of that hypersurface, and therefore represents Gromit invariance of that hypersurface. So how to prove this statement? So it's kind of sort of hypergeometric modification here. Yeah. So this red edition. First of all, so we will apply a combination of quantum Riemann-Roch theorem and what we just discussed in the previous page, this invariance of the cone with respect to differential operators. But in order to apply quantum Riemann-Roch theorem, we need that slight equivariant perturbation. We cannot talk about just the theory of the hypersurface L, but we need to think of the line bundle, or as a superspace. It's a line bundle over a projective space, a line bundle of degree L. We introduce action in the fiber of that line bundle with a circle action, just multiplication by scalars, and that lambda is a generator in the cohomology of CP infinity, which is the ring of characteristic classes of that circle, which that's complex circle that acts fiber-wise in that bundle. So therefore, what we're going to do now is let's look at this expression. So what we know is that if from quantum Riemann-Roch theorem, that if we consider in the symplectic loop space corresponding to projective space, the cone related to this equivariant, S1 equivariant theory of the supermanifold with odd part is the line bundle of degree L, then this new cone, so it's not this one, but that of that equivariant theory, that I think that's notation for that, for super manifold, is obtained from the cone for the projective space by some linear transformations, which I denoted by square, and it was the in the quantum Riemann-Roch theorem, in genus zero version of it, it was the Euler-Maclaurin asymptotics of this infinite product. So we take this, the lambda is the covariant perturbation of, so this is first-Chern class of that line bundle. That's first-Chern class of its equivariant first-Chern class of that line bundle. We take this infinite product, which is, it looks like kind of gamma function in some sense, over all m from 1 to infinity, and takes Euler-Maclaurin asymptotics, and that's what the square operator is here. But now what we do is the following. We consider the ratio of this to that, where the denominator is against Euler-Maclaurin asymptotics with a similar infinite product. There was the only difference that this operator of multiplication by the class P is replaced by this corresponding differentiation operator. So okay, so now let's try to do the following. So let's apply this. Okay, therefore this ratio is, it's a ratio of two Euler-Maclaurin asymptotics, similarly looking, with the only difference, and this involves of operators of multiplication by P, and this involves instead this kind of the deformation by differentiation in Novikov variable. In this example, it's one Q is there. So now let's see what happens when you apply two monomial Q to G. See that of course, the Euler-Maclaurin asymptotics interact with Q to G the same way as this infinite products, they kind of rigidly related. So it's easy to look at the right-hand side. So you see that this Z Q D Q, when you apply it to Q to G, it spits out Z times D. The effect will be the following, that this denominator, which is a product over m from 1 to infinity, now will be the same product, except that it will be not from 1 to infinity, but from LD plus 1 to infinity. Therefore, it will cancel with most of what is in the numerator, except that with the first LD terms. And that's what you get. Therefore, if you apply this to monomial Q to D, then you get Q to D times this, this finite product. The rest canceled out. On the other hand, if you think how does this ratio, this operator acts on points in the cone of the complex projective space, that what happens? The denominator is some differential. It's well, it's exponential. If you really look at what's Euler-Maclaurin asymptotics, it's exponential of some differential operator of the form we just discussed, of this type, and therefore it preserves the cone. And the numerator transforms it with the cone of this supermanifold. So therefore, the conclusion is that the following: if you have any point in the cone of the projective space, so therefore it is a sum over degrees Q to D, some coefficients. So that's just expanded as a series Novikov variables, whatever these are. So it is some point. Suppose that it's a point in the cone of the, so it presents Gromit invariance of the projective space. Then when you apply this operator to it, on the one hand, each term will be modified by this factorial product, as we just calculated. On the other hand, the whole thing will lie in the cone of that supermanifold, right? Because again, the denominator just preserves that cone, and the numerator transforms that cone to this one. And so, yeah, so the conclusion is that that therefore, if you, so that this expression lies in the cone of that supermanifold theory. But now, if you pass to the limit, non-equivariant limit when lambda tends to 0, then you get the invariance of that hypersurface of degree L. And the conclusion will be that this, so you see that quantum Riemann-Roch theorem to be applied, you need that equivariant perturbation. But once the result has a well-defined non-equivariant limit, that actually it computes that expression tends in the limit to Gromov invariance of the hypersurface. The only difference now is that on the hypersurface, P for projective space P2n is equal to 0, and in the hypersurface P2n minus 1 equal to 0. Therefore, this expression should be considered modular to P2n minus 1. So therefore, we have this mechanism which allows us from our examples from hypergeometric function representing in Gromov invariance of projective space, obtain some hypergeometric modification which actually represents Gromov invariance of the hypersurface. So that's what, and it's clear that this example kind of universal whenever you have so that doesn't matter what you replace CPN minus 1 with, just if you have such line bundle, and or you can apply it several times to complete intersections. So intersections of several hypersurfaces in a given target space, and this mechanism works. Questions about this? There is some comments. See any questions? No questions? Okay, let's extract more mileage from what we just figured out. It's called explicit reconstruction. You see that we have this, so this, again, it's explained in the example of complex projective space. Similarly, you can apply it to hypersurface of degree L or complete intersection in projective space, or actually what I'm going to say applies to every target space whose cohomology algebra is multiplicatively generated by degree 2 classes. For instance, toric manifolds or complete Clegg manifolds, but actually it can be applied to Grassmannians as well, but you need to modify it. Okay, there is some way to apply it in even beyond that situation, but at least to manifolds where the cohomology is multiplicatively generated as an algebra by degree 2 classes. So we have this cone representing Gromov zero Gromov invariance of the theory, and the role of it is that if let's get the graph of functions. So if you pick some point in the domain of the function, the space H plus, which is the Latam shift plus some Laurent series in Z, and lift it. Well, but what you do with graphs, right? Find a point above it in that cone, then the other component, the principal part of Laurent series, will split coefficients which are, I'm just referring again to this, what is it, to this definition of the big J function, splits this invariance, right? Now, in this explicit reconstruction, sorry, we actually will parameterize the entire cone. Yeah, what is it? We can parameterize the entire cone, not in this way, not by its projection along H minus to H plus, in a different way, but also parameterizing the entire cone by a space like H plus, like this one. And here is that what we can do. So suppose that we have some point again, parameterized how? Suppose that we know just one point on that cone. 1 point, it means that there is such a series in non-negative variables with some coefficients which don't depend on Q, and it's a point in the cone. Then we can apply a family of differential operators which preserve the cone, right? Therefore, which will move that point along the cone, but it will depend on parameters. What is written here is an example of projective space. So you see that the general homology class in the projective space is a monomial P2K times some coefficient and sum over K from 0 to n minus 1. So I use the operator which instead of P2K takes this differentiation in non-negative variable to the power K and applies this family depending on tau of constant coefficient differential operators. But I know what happens when I apply it to each monomial. So namely this derivative Q dq is replaced with d. So therefore what will happen really, just ignore this part for the moment, just see that I had my point, my small j function, this one, for the projective space. It is what we started with here, right? This one. That's my point. And now I apply this operator to it. What will happen, each monomial Q to D will be multiplied by this expression. It's e to the sum k from 0 to n minus 1, linear combination with parameters tau k, p minus dz. So instead of this derivative, I just have d, z to the power k. P is nilpotent variable, p to n is equal to 0. And I know that this whole family of points parameterized by tau lies in the cone. In fact, it's transverse to these ruling spaces of this cone, and therefore, if I differentiate them in direction of taus, which results in bringing down this monomial. So if I differentiate in tau k, I get this monomial, but if I multiply it by also by z, so I get a basis. Therefore, when I differentiate in each of tau k, I get a basis in the tangent space multiplied by z, basis in the ruling space. And if I take linear combination of these bases, those coefficients which are arbitrary power series in z, then I'll get the whole ruling space. And therefore, the whole cone is parameterized this way. So for fixed taus, this expression when this ck is just around arbitrary power series in z, so the coefficients are arbitrary, give me the ruling space, and when tau varies, it gives me the whole cone. Therefore, the whole cone is parameterized by by a bunch of power series in z without free term, because this minus z is a factor there, and a few more parameters which correspond to the basis in the cohomology algebra. So it is the same amount of data as points in that place space H plus. Therefore, if you from that, if you want to compute a particular Gromov-Witten invariant, which means what? So you want I said before, you want to take some point in this space. It's minus z plus t of z. Use it as the input in the correlators and compute, can leave that point there and compute the corresponding invariance. That's what by definition, that big J function tells you. It tells you all this invariance. So suppose that you decided what the t of z is, and you want to know what is that the corresponding invariance. So what you need to do, you need to take that expression. It is Laurent series in Z with coefficients depending on these parameters tau and coefficients in CK. Take the power series part, which is projected. So it is so projected to H plus along H minus. That's what this. So take that expression, take the power series part, and equate it to that input that you wanted, minus z plus whatever the input you wanted in your correlators will be there. Now, now you can run some formal inverse function theorem, which with given t's will compute the values of coefficients in ck and tau in terms of these t's. And after that, you substitute it into that expression. It will be something depending on these t's, and then take the minus part of it projection there. It will give you the value of the invariant, so that it's you can write a code. Actually have such a Python code that I tried for CP2. It works nice, but therefore you have in some sense you have at hand all the Gromit invariants in genus 0 from one point. And so if you have one point on the cone, you can parameterize the whole cone explicitly. It's explicit reconstruction. The word reconstruction comes probably from the old theorem of Manin and Kontsevich. They, in 93, I think, that they proved this first kind of theorem. They said that that looking at Witten diagram, Verlinde equations, they showed that if you yeah, so let's say, for instance, for a projective space or any space where you know the structure constants of quantum cohomology algebra, and you know that the classical homology is multiplicatively generated by degree to classes, then you can, from kind of recursively compute all the coefficients, all the Gromit invariants. And but here is kind of an explicit form of that statement. So it gives you all this invariance explicitly from one point in the cone. Any questions about this? Maybe so what I'm going to do next is to discuss a very specific application to a specific example of illustrating this full theory, which is that initial story with mirror conjecture that comes from the paper of Candelas, DeLuise, Green, and Parks. I was kind of assuming implicitly that probably the audience knows something about mirror symmetry, but maybe it was a wrong assumption, so that I maybe should start from the beginning and discuss what that mirror symmetry story was about, something that I could do in the very beginning. But maybe it's the right moment, therefore, to take a break. And thank you. So let's see how this general theory, how it works in the example that kind of sparked the interest of mathematicians to this whole theory. It's about quintic Calabi-Yau quintic threefolds in four-dimensional projective space. So about mirror conjecture in general, we should start probably from string theory, according to which our space-time should be 26-dimensional, of which 16 dimensions are super dimensions or odd dimensions, and 10 ordinary even dimensions. Out of these 10, 4 are the usual space-time dimensions, but there are 6 more, which string theorists say that it should be tiny, Planck should be of Planck scale, should be compactified, so it should be compact 6-dimensional manifold. But in order for the whole theory to work, it should have very special geometric properties. Namely, it should be complex manifold, and therefore complex 3-dimensional manifold, which is Calabi-Yau, which means that it carries a holomorphic, non-vanishing holomorphic 3 form. Differential 3 form. So it is, and there are many such Calabi-Yau manifolds, and kind of the physicists to see how many and which of them should correspond to our universe. But in any way, it is such a Calabi-Yau threefold is a 3-dimensional analog of elliptic curves. An elliptic curve, it's a curve which has a non-vanishing holomorphic 1 form, and all of them can be described as cubic curves in a complex projective plane. The 2-dimensional analog would be K3 surfaces. These are compact, complex, simply connected manifolds carrying a holomorphic 2 form. They all topologically the same and form one 20 parametric family of complex manifolds, but most of them are non-algebraic. However, there are many 19 parametric subfamilies of algebraic K3 surfaces, and one of them you can take quartics, degree 4 hypersurface in CP3, which will be in case with one of such algebraic 19 parametric family. Now, Calabi-Yau threefolds actually don't have even to have the same topology. They can have different, topologically different cohomology algebras. And one of such algebraic families is quintic, so degree 5 hypersurfaces in complex projective 4-dimensional space. So now the topology and algebraic geometry data for such a Calabi-Yau threefold is captured by what's called Hodge diamond. So from this picture, this P and Q, this HPQ is a dimension of it's a Hodge number, so it's a dimension of Q-dimensional cohomology of the manifold with coefficients in holomorphic P differentials, degree P differential forms. And so what is here? So it's sort of 4x4 squares, empty spaces are zeros. And this 1, 1, 1, 1, it is sort of the Keller dimension. So this one, it's a class 1 in cohomology. This stands for Keller form, and this is square, and that's a cube. So the symplectic form is square and this cube. These are the classes with P equal to Q. So it's 1, 1, 2, 2, 3, 3. Now here, this one is it's H 0, so it's global sections of the sheaf of holomorphic C forms. That one stands for that holomorphic C form, which makes the manifold Calabi-Yau. Now, this is H21. It's a number of parameters. So this stands dimension of tangent space to the moduli space of complex structures. So when you in this example, so it's about quintics, threefolds in this particular family. So you can see what this one is. If you just consider all monomials of degree 5 in 5 variables, then there are 9, choose 4 of them. It's 9 times 8 times 7 by 6 divided by 24, it's 126. But if you identify those polynomials which differ by linear transformations in the underlying 5-dimensional projective linear space underlying CP4. It's therefore this 5 square, it's a dimension of GL5. Then the difference will be 101. And so that's therefore this the whole family of complex structures obtained by just all degree 5 hypersurfaces in the projective space up to projective transformation. Now the mirror theory says is that the mirror conjecture says it should be, so given such a Calabi-Yau threefold, there is another a family of Calabi-Yau threefolds where these two diagonals, the one corresponding to this one corresponding in some sense symplectic geometry, and the other one corresponds to complex geometry, to variations of complex structures, the periods of holomorphic forms which distinguish such structures, that their roles are interchanged. That is, this table is flipped over. And the myth is that it was discovered by one of the myths that was discovered by an accident. So people tried to run some computer programs that generated these Hodge diamonds for Calabi-Yau threefolds, and someone messed up some signs there, and they suddenly discovered a parallel tree of such Calabi-Yau threefolds where these diagonals were flipped over. In particular, for this example of quintic threefolds, it is so the mirror is known or was known at the time when Candelas, Deleuze, Green, and Parks wrote their paper, and that's how it can be described. So first, one considers this equation. So they take the product of coordinates equated to zero. They're homogeneous coordinates in the projective four-dimensional space. So there are 5 of them. Of course, this is just a union of hyperplanes. It's a singular. But now we perturb it with this term. So this is just a parameter here. And you get a one-parametric family of typically non-singular quintics, which actually are symmetric, because if you multiply this axis by fifth roots of unity, then this expression is preserved. But if the product of the root of unity is 1, then this is also preserved. And therefore, there is this group of z to z5 to the power 4, so this roots of unity, which preserve this equation. And you can take the quotient of this quintic by it. And this quotient will develop singularities at some fixed points of these transformations, but you can resolve the singularities. And when you resolve singularities, you create a lot of 1-1 cycles or cohomology classes. And so the result is that what will happen, there will be 101 dimensional space of Keller forms or symplectic forms there. But there will be only one parameter of the complex structure, namely this lambda will be the parameter of the complex structure, but it's still Calabi-Yau threefold. Therefore, this is stationary. There is this four-dimensional 1-1-1-1 four-dimensional space, which altogether is middle dimension of the cohomology. Therefore, there are 4 independent cycles over which you can integrate holomorphic three forms there. And there are a lot of different Keller forms, but in symplectic topology, it doesn't matter which one you choose when you start deforming symplectic structure. The symplectic topological invariants don't change. Now, the point of this mirror symmetry is that actually the physicists believe that it's not just there are such these diamonds are symmetric to each other, so they're totally topologically different manifolds, but somehow strangely related to each other. So, but the physicists assume that there are some quantum field theories, one related to symplectic topology there, the other related to complex geometry there, or maybe it's two sectors of the same quantum field theory. And these two sectors are interchanged. Therefore, therefore, symplectic topology on one manifold is equivalent to complex geometry on the mirror. And from that, one can try to extract some mileage. Say computing, say, Gromit invariance of one of quintic threefolds using complex geometry of the mirrors. That's a starting idea. But so let's look at symplectic topology or Gromit theory of such Calabi-Yau threefolds. This is the Riemann-Roch dimension. The Riemann-Roch dimension of the moduli space of stable maps of genus G. So that's a general formula we already discussed with you, that this 3G minus 3, it is, actually no, it should be plus n. I think that it's incorrect because it's true for 0 mark points when there are no mark points. So therefore, without mark points, there are 3G minus 3 parameters of complex structure on the curve, but then for a fixed complex structure on the curve, you can ask how many, what's the dimension of variations of the map itself, homomorphic maps of that curve, and it is given by Riemann-Roch formula, which is for each unit of dimension of the target space. It is what's the classical Riemann-Roch formula tells you it's a degree minus G plus 1. And so that's what this formula tells you. And this degree, of course, is just the integral of first-chain class over the evaluation on the homology class of the curve. But so in Calabi-Yau threefold, this is zero because the first-chain class is zero. It's what it means that there is non-vanishing holomorphic volume form. Holomorphic three form means that the first-chain class is zero. And the dimension of the manifold is 3 means that this is zero. Therefore, the expectation is that if the complex structure is generic enough, or this is almost complex structure on the Calabi-Yau threefold is generic enough, then the curves in genus G in any degree will appear discretely. So there is a discrete number of them. They are isolated. The modular space has dimension 0. And so let ND means the number, this is actually a virtual number. So it's what it's a virtual fundamental determined by the virtual fundamental class of the corresponding modular space, but it's therefore it's this virtual number of degree D rational holomorphic curves. I care about genus 0, so I'm talking about rational curves and don't introduce any annotation for genus. Now, if you know these numbers, that's all you need to know to compute quantum cohomology and compute Gromit invariance. You can imagine that the modular spaces are very simple, just points. So there is not much intersection theory there, but that's what turns out what the small j function looks like in this case. So that's the standard factors, dilaton shift. Okay, so this is expression, and d, it is that number, and for each degree d, positive degree d, for each such an isolated curve, there is this contribution. P is the hyperplane class in the quintic, therefore P to the power 4 is 0. It's a three-dimensional manifold. It's you intersect hyperplane with hyperplane as hyperplane, you get actually 5 points in the quintic threefold because the degree is 5. But intersect it with one more hyperplane, you get 0. So P to 4 is equal to 0. So still there is this kind of sum over k greater or equal to 1. So it's not just, so the curves of degree d should contribute to q2d term, right? But you have here a contribution to kd. The reason is that once you have a rational curve, isolated rational curve of degree d, it actually comes together with multiple covers of it. It can have cover degree 2, 3, etc. And so you need to take into account the contributions of these multiple covers and the corresponding Gromit invariance. It's not a hard problem to solve, and the formula was for the first time found by Aspinwall and Morrison using somewhat naive method, but then it can be confirmed by many other means. In particular, you can use this quantum Riemann-Roch and quantum Lefschetz logic, namely, if you have an isolated CP1 sitting in the quintic threefold, then for generic one, the normal bundle will be equivalent to of -1 plus of -1, the homomorphic bundle. And so really, this contribution comes from Gromit invariance of the total space of this bundle. So we're discussed with you complete intersection of supermanifolds, but this is a parallel story where you deal not with a supermanifold, but rather with ordinary bundles, even bundle, vector bundle, and study Gromit invariance of the total space of it. It's non-compact, but still you can define them using equivariant homology. And there is a parallel theory of twisted invariance, and so that the whole story it's known what the result is, and that's what it amounts to. So it gives this kind of contribution that takes care of multiple covers of each curve. So one usually treats it as a solution to looks at as a demodule generated by, so it's some one point on the cone of the theory, but it generates some demodule, and if you differentiate it twice, apply this kind of second differentiation twice to it, then you pick this factor, cancels out here, so you'll get this expression. And I think this is called this series Yeah, you see that when you cancel that, there will be sum of geometric series. That's why you get QD over 1 minus Q2D. And they call it Yukawa coupling. But anyway, therefore, if you divide by that Yukawa coupling, you just have just P square. It doesn't depend on Q. If you apply that operator twice again, the D is this differentiation operator, then you'll get zero. Therefore, this function satisfies this second, fourth order differential equation. It's called kind of self-adjoint differential equation. In any case, well, this function Q of Q, it encodes all these numbers. If you know it, you know what these numbers are, but also, of course, the solution to the differential equation knows what the coefficient of it is. If you know this point on the cone of that theory, then it also tells you what these numbers are. Either way, that's what, in some sense, that's what you want to compute for your Calabi-Yau threefold in order to know genus zero growing with invariance. Questions? Is it a familiar story or something? What do you think? Is it, Daniel, is it something that everyone in the audience already knows? Or
Well, we have covered a lot of talks similar, but I don't know what is the background or if everyone of the audience attend.
no.
So it's
Okay. So now let me talk about this example of kinetic threefolds, kind of the three treatments of it. So one is in the original paper of Candelas, De Leosa, Green, and Parks. The other is how it would look like from the point of view of S1 equivariant, that heuristic picture of S1 equivariant Floer theory on the loop spaces that we discussed with you in, when was it, in the first lecture? And the third one, how it looks from the point of view of quantum Riemann-Roch quantum Lefschetz theorem. So what Candelas, De Leosa, Green, and Park said the following. So let's take, we know the mirror of kinetic threefolds, that one parametric family of Calabi-Yau manifolds, and there is a holomorphic volume form. You can explicitly write it down, and you can derive differential equations for its periods. Therefore, if you integrate that three form over cycles, and there should be four independent cycles, because this Hodge diamond, right, is for this mirror quintics is like that, and so this diagonal, it's middle cohomology of it is four-dimensional, and this three-dimensional this degree three form can be integrated over four independent cycles, but the integrals will be functions of lambda, but they will satisfy the same differential equation. It will be four solutions of a single kind of generalization of Picard-Fuchs equation, and that's how you can derive the differential equation. That's how it will look like. It's fourth derivative in logarithm lambda, and there are this, I don't know, 5 lambda, and this 5 plus 1, 5 plus 2, 5 derivatives plus 1 from plus 2 plus 3 plus 4. Well, this is fourth order differential equation. So particularly this, one of the solutions is this hypergeometric series. It's a 5D factorial divide. I think it's written ambiguously. So it's 5D factorial divided by d factorial to the power 5, lambda 2d. And there are three other solutions to that equation. They involve some logarithm of lambda as well. Now, from the point of view of that paper, Candelas et al., this parameter lambda has no intrinsic meaning. It is just some parameter. So there is one parametric family of complex structures in this Calabi-Yau mirror threefolds, and it is just some coordinates that you choose there. It's you can choose any coordinates there, right? But the expectation is that if you expand so that near the singular point lambda equal to 0 there, is that the that the series solutions, they somehow supposed to capture Gromov-Witten invariance of the quintic. They should be equivalent to to this differential the differential equation and its four solutions. It's because there is that's the essence of mirror conjecture. You believe that complex geometry on mirrors, it captures the symplectic geometry on the original manifolds. And so therefore what they do next, they construct some canonical basis of solutions. So they first examine the monodromy of the solution near lambda equal to 0. It is unipotent. They take some Jordan basis there. So they construct some canonical basis of solutions. And in particular, they create, in terms of these periods of the reform, they create a canonical parameter, the canonical variable, which already intrinsically related to variation of complex structures, similar how in elliptic curves, right? There are two periods of holomorphic one form on elliptic curve, but if you take the ratio and so you can construct the canonical parameter on SL on the modular curve near the cusp using the periods themselves. So kind of parameterizing by points in the upper half plane up to translations. So therefore they construct, the conclusion is the following, that in order to get that J function which counts invariance, you need to do such a strange procedure, they say. So you have this, in particular basis, you have these four solutions which you can write as this, it's not what they say, but it's what in my notations would be. So it is vector valued functions with values in the cohomology. P is a hyperplane class. And so you divide all of them by I naught, by this series. So the coefficients will be 1, then the ratio of them, and then two other functions. And then you take this ratio for the logarithm of the Novikov variable. So the exponential of it is the Novikov variable. And then you make this change of variables, replace lambda. That depends on lambda. Replace lambda with using this change of variables, and then you get these functions which already now in terms of Novikov variables, they know these numbers. So from them you can reconstruct the numbers. It's pretty strange procedure, and this change of variables is called the mirror map. The motivation why, so the words that string theorists say around this algorithm, they say something about renormalization group acting somewhere, and well, some strange words, but that was kind of fascinating picture for mathematicians. You want to know rational curves on quintic threefolds, and instead you should take some completely different manifold, compute some periods, and do some strange manipulations with it, including some kind of change of variables involving infinitely many coefficients, and then somehow miraculously after that the numbers of curves on the original manifolds come out of this. So that it's so the question would be how one can justify such a wild statement. Now let's see how it looks from the point of view of S1 equivalent Floer theory. Should we recall anything that we were studying, we're doing there? So you say that what we let me try to go back and see where yeah, so that's a page we were discussing. First of all, S1 equivalent Floer theory on loop spaces, and it was the more theory for action functionals, and action functionals with multiple values, and were deck transformations would stand for what we understand now as Novikov variables. Yeah, and figured out that there is some D-module structure there. But in fact, you can get more from the theory, especially when you look at specific examples such as projective spaces or hypersurface in projective spaces or toric situation for toric manifolds. Namely, that Novikov variables are these deck transformations on the covering of the loop space, but so it's a lattice of deck transformations, but there is a bigger lattice acting there, namely, which is that if you think of say projective space as a toric manifold, there is a maximal torus of the space Cn acting there. So the projective space is obtained by factorizing by the diagonal circle of the torus, but still there is a whole torus acting there. And the torus contains its pi1 lattice. There is a torus, but there is also pi1 lattice of it. There is a lattice of one parametric subgroups in the torus. And when you pick some one parametric subgroup, or just a loop, some maybe non-contractible loop in the torus that acts on it, you can pointwise act on the loop space. You just can take a loop in your manifold and pointwise apply a loop in the torus which acts on the manifold, and you get a new loop. So you get bigger lattice of discrete transformations, and so therefore when you do some Floer theory, or think of some de Rham Floer theory, and various depth transformations and so various operations there, you can actually decompose that de Rham complex into characters of this lattice acting there, and get from this kind of more fine information than just the one you get by just computing this Floer equivalent Floer, this one equivalent Floer theory and the corresponding G-module, and it gives you. And then I'm saying something not very very clear, but the point is that there is more structure there that allows you to actually construct the mirror itself. So you see that the let's go back to the page we are currently discussing. It's so what we want to compute is maybe some D-module corresponding to that Floer theory, but the mirror information, it requires more geometry, because what you want to represent is that the D-module solution of some differential equation, you want to represent them as integrals over something else, like here like periods. Therefore, you need additional variables and more geometry. And it turns out that from that Floer theory, if you use this lattice of the pi1 lattice of the torus acting there, you can obtain that more geometry, and that's what it leads to. Therefore, if you start with complex projective space CP4, then it gives you such an complex oscillating integral. So what's written here is, therefore, there is this function u1, etc., plus u5. In fact, in the theory that's used, in some sense, they come from, if you think of, say, momentum polyhedron of the projective space, which is a simplex, with respect to the torus section, then there are this invariant divisors corresponding to the walls of that momentum polyhedron, and in some sense that U's are equivalent cohomology classes corresponding to them. And you have therefore this function which kind of corresponds to the equivalent first-Chern class of the projective space. But that five-dimensional space in which this linear function lives is fibered over one-dimensional space with variable q by this formula. So q is equal to the product of these variables. It comes from sort of embedding the diagonal circle by which you factorize to get projective space into the maximal torus, which acts on the space C5. So there was this kind of corresponds to inclusion of tori or corresponding pi1 lattices. And so there is this integral. So this is a sort of volume. So the fibers over this projection from 5-dimensional space to Q, that fibers are complex tori, and this is translation invariant volume form there. And this is oscillating integral. This letter Z, right now it's a small parameter. If you want to say, examine the symptotics of such integrals near critical points of this function is restricted to the fibers of this vibration, then this that will be the parameter Z will tend to 0. It is that same Z which already occurred many times in different roles. It was the generator in the cohomology of BS1, the classifying space of that circle, which acts by rotating loops, or it was a placeholder for psi classes in Grom-Witten theory. But it's that same Z now it appears in the new role, or that Z that plays the role of Planck constant in differential operators like this one. But now it plays the role of this small parameter in the phase function like Planck constant gain. And so it's not hard to see that this such periods, again, there are some cycles to be chosen in this in such tori. And it's a separate question what kind of cycles you need to take. You need to do some kind of Morse theory for the real part of this function in the exponent. But anyway, the integrals over all periods, and there are 5 of them, 5 different independent cycles here, they satisfy this fifth order differential equation. This D is Z times the logarithmic derivative in Q, and differentiated 5 times, you get Q times that. It is again in the equation which we already saw many times. It's a symbol is a relation in quantum cohomology of CP4. It's P25 is equal to Q. That's a relation, and that's what. So this equation is what we would get from that linear sigma model picture that we discussed in the context of Floer S1 equivariant theory. But now it comes with additional realization of this solution to this equation in terms of such integrals. Now, the logic of mirror symmetry tells us if you want to pass from this projective space to a hypersurface, in it, which is an anti-canonical hypersurface, so it will be Calabi-Yau 3-dimensional manifold here, then it's on the one side of the mirror. Then this is a mirror of complex projective space. So that this oscillating integral, it is, and its periods are, and that this integrals and differential equation which satisfy. So this lives on the it's kind of object of singularity theory rather than complex geometry, but nevertheless it's the other side of the mirror. It's a mirror to the projective space. But now if you want to pass to on the one side to anti-canonical hypersurfaces, and here you need to do the following. This integral can be represented as the iterated integral. We first integrate over the level of this function, equate to a constant, and then do kind of a Laplace transform that this expression suggests. And then this interior integral, when you integrate over the level of the function, that's the mirror of supposed to be the mirror of the of that anti-canonical, that Calabi-Yau hypersurface. And so that's what it is. Therefore, if you equate this to 1, so take level 1 of that function, that then this form divided by the differential of that equation, it's well-defined form on what? On this now 3-dimensional manifold when the product is equal to Q and the sum is equal to 1. Now let's see what these equations, what's the geometry behind these equations. Let's recall the equation of mirror quintics, that one parametric family depending on the parameter lambda. That the equation was as this was equated to this, right? So now let's take this ratio and equate it to 1. It's the same thing, right? Now, if you consider this expression, that is what is lambda 215, 1 of the x's to the power 5 divided by the product. So there, what is written is if you call this u's, it's u1, etc., u5. Then what's written here is the sum of u's is equal to 1. And if you multiply them out, then you will see that everything cancels, and you get lambda. Therefore, if Q stands for that lambda, then the system of equations is the same as actually sort of a fine chart on the quintic, on the mirror quintics. These expressions are invariant with respect to that group, discrete group of roots multiplication by roots of unity. And therefore, these expressions, so these U's are coordinates on the quotient of those quintics by this group Z5 to 4 of these roots of unity. At infinity, there will be some singularities that in principle you should resolve to get the mirror quintics, but you don't need to do that if all you care about is just computing the periods of holomorphic form, because this is the holomorphic 3 form in this affine chart. And all the cycles that you need to compute its periods are sitting in this chart. So it doesn't depend on how kind of don't involve compactification or resolution of singularities, doesn't change anything. And therefore, this I, it is effectively the same thing as literally this solution, this I, solution to these equations. So, but in a way that we get this mirror picture from some upgrade of linear sigma models that we discussed before, and from theory, S1 equivalent Floer theory on loop spaces. So it kind of comes from the same side of the mirror where the complex projective space and quintic threefolds lie. Now let's see how this story looks like from the point of view of our Gromit theory, quantum Riemann-Roch, and quantum Lefschetz. So we first obtained this expression. It was L that time, not 5, but L. It was in general projective space and some hypersurface degree L, but this time we have CP4 and hypersurface of degree 5 there. We obtained that expression as by doing that heuristic theory of S1 equivalent Floer theory on the loop spaces. Yeah, so it is a solution to so if you now consider this differentiation D as it should be in Gromit theory, some twisted multiplication differential operators twisted by this matrices multiplication by P, then it does satisfy this this equation. So it is the same except for this change of the representation of the algebra of differential operators. It's the same differential equation to which this satisfies or this period satisfy. But what we know now from quantum Lefschetz theorem, we know that this expression literally lies on the cone of the theory of this cone corresponding to quintic threefolds. That's what we see. It is that very same hypergeometric modifications as we discussed before. So we start here. Start with this small j function for projective space. We do this modification, and then what we prove that establish that it lies on the cone of the degree L hypersurface, and so therefore this expression lies there. Now P is an nilpotent variable. P to 4 is equal to 0. Therefore, if you expand it, represent it as one should in terms of the basis in cohomology, 1 pp square p cube graded basis, then that's how it will look like. So it will, that expression will look like that. There, I know I1, I2, I3 will be some series in Q, and Z will occur only in this way. You can see here that it's expression rather simple, so that I node will be exactly this this hypergeometric function, except that for lambda there will be Q there. and you see that what is the difference now with Candela's de la and Park's picture, that for them that variable q look like kind of that lambda at that time just random parameter having no intrinsic meaning, but now and that the whole expression, therefore that whole happy geometric solutions, they themselves didn't have any meaning in the theory, so that you could extract from them the required information by themselves. There was just some functions written in some arbitrary coordinates, coordinate representing the variation of complex structures, but so the coefficients of those series in lambda didn't make any particular sense. Now we see that it's actually not the case, that this whole expression does represent ground width invariance of the quintic. It lies on the cone at some point on this cone, and except that it doesn't represent the invariance that you were looking for, because you need to take its projection to, so you need to take its part that it is this part. So this will be the part in H plus, right? So it is minus Z times something plus 1 times this Z cancels out P. So it will be power series part of it. And that will be the input, determine the input in correlators of ground width in theory, for which this part represents the answer, the invariants themselves. Therefore, this expression represents ground width invariance at the point it itself wants to, that it itself knows. It's determined by this projection of the point in this direction along to H plus along H minus. But you wanted not that, you wanted the small j function, and now let's see the small j function, or just function how it looks like. That's that's the definition of it. It should start with -1 times z, the dilaton shift, plus then add just some homology class of the target space, and then there will be invariance where this homology class will determine the input. That is definition of it. So now this expression doesn't have that form, because, for example, because it doesn't start with -1 over z. It starts with 1 minus z times I naught, where I naught is that hypergeometric series. But the whole thing is a cone. Therefore, and this is from that point of view, just series and numeric variables. It's a constant. Therefore, you just can divide by it. If you want to make this coefficient 1, then you can divide by that function, and you still remain on the cone. That's what that operation meant. So that you divide by that, and you'll get this expression which still lies on the cone. Now, this term, it's a degree 2 homology class P times something. It's some constant from the point of view of ground width in theory, so it's a series in Q. So this is this tau, and that's why you need that mirror map. So that's the input tau in the correlators, which this whole expression computes. And if you make that change of variables, then this expression, this part will compute for you that part, the ground width invariance corresponding to that tau. And therefore now that strange procedure, that fascinating procedure of somehow normalizing the solutions, dividing something and making change of variables, it becomes perfectly transparent, because it just means that you, from one point on the cone, you actually could generate the whole cone using explicit reconstruction, and then in particular pick this canonical section, which is a small j function, or you can just do this procedure to get one point on that small j function, and it already remembers all the numbers of rational curves there. So that so we've kind of proved the mirror formula. I wouldn't call it a mirror conjecture, because mirror conjecture is kind of, it's a much more general bunch of rather vague and powerful ideas. There is homological mirror symmetry. There is equal equivalence between complex geometry and symplectic geometry on mirror manifolds, and there are many aspects of it. This is rather some I would call it particular mirror formula for quintic threefolds. Formula that comes from mirror symmetry, but at least we have a proof of it. It's not the first proof; it's probably the seventh one, but nevertheless, it's based on. Based on quantum Riemann-Roch formula and something else. We use all the intrinsic identities of Gromov-Witten theory in genus zero and the divisor equations. And altogether, they produce this result. And that's apparently what Maxim Kontsevich wanted to do when he tried to apply Riemann-Roch formulas to this situation. Any questions? No questions. Maybe we do have time to discuss that what I mentioned, that Virasoro conjecture. It's kind of perpendicular to what we're discussing here, but it is a nice illustration of this symplectic loop space formalism and how it simplifies many things. Actually, Virasoro conjecture, it's one of the maybe the general outstanding conjecture in Gromov-Witten theory. Kind of, it's supposed to be applied to all target spaces, and it's proved for some classes of target spaces, for instance, for so-called semi-simple target space for which quantum cohomology is semi-simple, and it can be proved using Telemann's classification of all such cohomological field theories, semi-simple cohomological field theories. But in general, it is not proved, and that's what it is about. So again, this is a formula for the dimension of the virtual fundamental classes, dimension over complex numbers of modular space of stable maps. And you imagine when you want to compute some particular Gromov-Witten invariant, so you want to reintegrate something or some cohomology class over evaluated on this fundamental class, to be non-zero, that the answer, for the answer to be non-zero, you need that what you integrate, the degree of that class, matches the dimension of the virtual fundamental cycle. There is a gradient in cohomology, and so that the dimension should match. Otherwise, it is zero. And this imposes some constraints on the generating functions. So if you try to express these constraints explicitly, then yeah, so well, one thing what you need to do, you need to the letter z, for example, need to assign the degree 1. So for instance, if you have this general input in correlators, and T0, T1, T2 are just cohomology classes of the target space, and they have their natural degrees, but this is a placeholder for the psi class, and therefore in complex units, it should have degree 1, so that in the real units, it's the first-chain class has degree 2. But then, so the way how one can express the fact that the generating function can abide by this grading constraint is the following. So first, there is this, so that you can say that there is some operator which it itself acts on the symplectic loop space and corresponds to some quadratic Hamiltonian, and if you quantize it, that quadratic Hamiltonian L naught hat annihilates the that quantized operator annihilates the total descendant potential. So that's a way to formulate this grading condition, and this operator, the ingredients are the following. So that this is, well, it's what we see it is. So it's ZD over DZ. This 1/2 is just, this whole expression can be understood as root of Z, the derivative, and then root of Z. So it is something that is anti-symmetric. So it's kind of the average of ZD over DZ and D over DZ times Z. So it is something anti-symmetric with respect to our symplectic structure and symplectic loop space. So it therefore generates some infinitesimal symplectic transformation. It can be quantized, it corresponds to some quadratic Hamiltonian, can be quantized. Now, this mu, it is, yeah, in some sense, therefore, it is kind of, it's needed there to take into account that this letter Z is a placeholder for psi classes, so that it's a reflection of that. That mu reflects the gradient in cohomology, namely, imagine that you have some homogeneous base in cohomology, and you just have the diagonal matrix multiplying each base element by the degree, say in complex units, right? So half of the degree, except that it's, as in Hodge theory, it's shifted to the middle dimension. Therefore, in the middle dimension, the class of middle dimension multiplied by 0, but therefore it is the gradient operator minus half of the dimension of the manifold. And because of that, it is anti-symmetric with respect to the Poincaré pairing. It's because it kind of acts on symmetric degrees. If 1 degree is multiplication by k, then symmetric degree is minus k, then it turns out to be anti-symmetric with respect to Poincaré pairing. And as a result, it itself is an infinitesimal symplectic transformation with respect to symplectic structure. And this it's 1 over Z, and this is a multiplication in classical cohomology by the Fortune class of the tangent bundle, and it is there to reflect this part in the dimension of the modular space. That's where it comes from. But anyway, all these three terms are anti-symmetric with respect to the symplectic structure, and therefore this operator L considered as a linear operator or defining a linear vector field on the symplectic loop space, it corresponds to some infinitesimal symplectic transformation to quadratic Hamiltonian, can be quantized. And the fact when you do that, then this condition that L naught hat D is 0, that would means that D obeys the grading constraint. But now you can introduce more operators, namely consider these operators L naught, Z, L naught, Z, etc., Z, L naught. There are MZs and M plus 1 L naught. And even for M equal to minus 1, where are no L naughts, but there is minus 1 Z, therefore it is 1 over Z. That is a string operator. So these operators, you see that this L naught is, with respect to Z, is differential operator. So this is high order differential operator. But if you start commuting them, they commute as vector fields on the line. So it is, actually it's wrong to call it Virasoro algebra, it's a half of Virasoro algebra. It is the algebra of differential operators, derivative x times derivative x squared times the derivative. They commute as these operators. It's easy to check directly just from this form. So essentially from the fact that how d over dz commutes with z. So the rest is the rest, that's only non-commuting things there. Okay, so the conjecture, the Virasoro conjecture, due to Iguchi, Hori, and Hyung, says that if you consider these operators, quantize them, and apply to that total descendant potential, then you get 0. And in general, I said, so therefore the first one is satisfied. It's because the string equation, the next one with index 0 is satisfied because that's what it means that that the dimension of the integrand should be equal to the dimension of the fundamental cycle. And essentially you need to prove two more, L1 and L2 constraint, because the rest follows from the just obtained by commutators in that algebra. But it's in general, it's an open conjecture. However, it's known to be true in genus 0, and it's a theorem by Liu and Tian. And in their paper, it's something like 20 pages of computations, deriving it from other identities of Gromit theory, from the string equation, dilaton equation, and topological recursion relation. Now, here is one line, essentially maybe 2 lines instead of 20 pages, which shows how to prove. So why is this in genus 0 this conjecture is true? So really, in genus 0 it means that if you consider vector field in the symplectic loop space corresponding to this linear operator Lm, then this vector field is tangent to the cone, to the Lagrangian cone, which is a graph of differential of generating function f naught. And that's why. So you take a point in that Lagrangian cone, and it lies in some ruling space, z times t, where t is a tangent space at that point. Now you apply L naught to it, then you get point in the tangent space. It's because that's what it means that the grading condition is satisfied, right? That L naught is a vector field tangent to the cone. But then if you multiply it by z, then you get again point in that same ruling space. But therefore, if you apply L naught to it, then you get again a point in the tangent space. But then you multiply it by z again, you get a point in the that same ruling space, and you apply L naught again, then you get again point in tangent space. And after m steps, you get that Lm times f lies in the tangent space. And that's what it means, that for every point in the cone, the LMF, so the vector of that linear vector field at that point is tangent to the cone at that point. The end of story. Yeah, it's kind of it's tempting to try to generalize this to higher genus, but somehow it's not clear how it could work, because here it's a composition. These operators are compositions of some simple operators, but when you quantize it, quantization is a homomorphism of Lie algebras, but not of algebra, so that you don't get any mileage from that. Any questions about this or anything else? Then maybe it's time for me to stop and